is possible to start a career by exploring, excursion above its minimum of a one-dimensional Brownian path, and nevertheless um, still get interested later on in other aspects and parts of mathematics, and sort of he was one of those who sort of showed that probabilistic ideas could permeate in other areas, would be useful and fruitful to use, and he was somehow, with a couple of others, one of the pioneers in that direction, and it's very inspiring. It's somehow ironic that, I mean, in some sense, it's very nice that this is basically my last day here in Orsay. I'm going to hand back my key to the later, that I have the opportunity to pay tribute to Jean-Michel and his very Swiss-type backpack always that you meet in the RER. You know, he has a always very fully packed. He's always transporting back and forth tons of papers and books, and I was always wondering how his back is actually coping with that, because it's always the backpack is actually hanging, with one, so he's always doing everything wrong in terms of for his back and his health, but it doesn't seem to harm him in any way. I don't know what, but yes. So I want to add that it's really great to have this conference here to remind us that this place is the, in some sense, center of way of how to do mathematics and how to. And to have Jean-Michel at the end of the office, half open at the end of my corridor during all these years was, one of the very nice feelings when I was opening my office. Anyway, so it's a sort of daunting thing to speak in such a conference because, as Jean-Michel very well knows, because we have been sharing this great pleasure to be part of the executive committee of the International Mathematical Union, there's always the question of how to tell the speakers who have to speak at an ICM that they are supposed to give a understandable lecture. And I somehow feel that in the present case it's even worse, because we have this sort of amazing setup of speakers. Each one is telling you proofs of amazing things, and so it's even more impressive somehow at an ICM, I think. And nevertheless, we are sort of, the audience is somehow mixed. Some people are specialists of one field are showing up, and nevertheless sort of it's a and so in particular it's clear to me that the audience is not made of just of probabilists or specialists of the particular topic I'm going to tell about, even though you've probably heard pieces of it and patches here and there. So I decided somehow, given the fact also that there are going to be two very closely related talks, the one by Scott and the one by Julien, who are both going to, well, it's not that closely related, but still you will see many non-trivial intersections, and they all have to do with, in some sense, two-dimensional randomness and involving complex analysis. So, so what I will try to do here is not to focus on the, of course, I want to clearly make it up to what we are try to describe what number of us are trying to do these days on this topic, but most of the talk will be try to present you the global overview and to some perspective on why, why we are trying to do certain things, and try to explain certain ideas and put into perspective a little bit. And so I almost changed my title, but I knew it was not, I gave my title, which was a generic title, which I knew could fit anything. And in fact, I will be mostly focusing here on the carpets part of this talk, and namely, this idea will be to say, what can we do when you want to do analysis in general, or trying to define, conformal invariance and analysis involving conformal invariant ideas in fractal domains of dimensions that are sort of subsets themselves of the plane, and what one can do and how these objects, define what you can do. What you will see later in the talk by Scott is basically how to define sort of geometries in a sort of geometrical meaning, and will be sort of a counterpart here. This is sort of a down-to-earth question about here is a fractal, what can you do in there? And so I will be mostly recalling background. Some of the background is actually quite recent, but so I'll just mention very quickly features of planar Brownian motion. There's a Schramm-Leuven evolution of parameter 6 and percolation. I will recall some results that have to do with analysis in deterministic fractals, Sierpinski carpets, for instance, and the questions related to uniformization and conformal invariance for such domains. So basically, Riemann's mapping theorems for such domains. And then I want to make a brief description of one family of fractals that we've been studying with Scott, which is a nice way to define, a way to define random fractals that are actually much more tractable to work on than the deterministic ones, and you will try to explain to you why. And then basically I'll try to describe ideas how to play what you can do in these objects and what type of structures you can start discovering. So I will try to use the blackboard in order to make it a bit more dynamic when you see the pictures. So just recalling two nice conformal invariant processes that have, so this is an old stuff, but so first one, of course, is planar Brownian motion. And this is a nice two-dimensional process. As you all know, it's sort of this random continuous path. And this random continuous path has two very nice properties. The first one is that, first one is continuous, which is actually not trivial. The second one is that it has this sort of Markov property that the way it evolves here does not really depend on the domain it lives in. It just evolves locally without knowing where the boundary of the domain it lives in actually is located. So it has sort of some locality property. And in 2 dimensions, it has an additional property which is conformal invariance. So basically, if you are sitting in a domain D, and then you transform conformally the domain, you draw this blue path, this picture here, this blue picture, random blue picture, which is a Brownian motion started, say, from Z0, stopped when you exit this domain. So this defines your random picture in that domain D. And when you distort this random picture by conformal transformation, so you change D into some other domain D prime, you distort the blue part as well, but the blue part is still a Brownian motion in D prime. And this is, of course, very important. So now the second nice object that I want to, of course, there are many other nice objects, but is the Schramm-Leuven evolution with parameter 6, which has been introduced by Schramm in 1999. And this process, I just show you, the picture, has also a local property and conformal invariance. And the way to understand what this SLE6 process is to consider this picture where you toss a coin at each side and to decide whether it's white or black with probability 1/2. And then you're looking at basically in this picture at this, you're exploring the sort of the boundary between white and black in that picture. And exploring a boundary between white and black in that picture is a purely local feature because you are, in order to, when you walk here, you have to know the state of the cells nearby, but you don't need to know in what domain you're playing that game. And when the mesh of the lattice goes to 0 or gets very small, you get a picture. This is now how a boundary between white and black looks like, and this converges in the scaling limit, has been proved by Smirnov, to a continuous object, which is this Schramm-Leuven evolution with parameter 6. And in the proof of Smirnov, in order to prove that this converges when the mesh of the lattice goes to 0, you're actually using the fact that this curve is conformally invariant in a similar sense than what I described to you here for Brownian motion, and clearly it has this sort of locality type property. So you can define it locally in a domain, and so what I mean is that you can use both processes in order to explore the domain, right? So you start, you are sitting in your domain, you say, okay, I launch a Brownian motion from where I am, but I'm sort of discovering the territory I'm working on simultaneously with right. I don't need to know what territory is, how it is, in order to define it, and same for the Brownian motion. Okay, so this is just a quick background, and these two features. So this is really, I try to be quick, but these two features, the fact that the Brownian motion and the SLE6 share this locality plus this sort of property, shows that, in fact, they give rise to similar shapes, or actually the same shapes. So in the scaling limit, what you know is that if you take a large percolation cluster like here, or if you take a long Brownian loop like here, if you look only at the outer boundary, if you only look at the outer boundary here, so this picture and this picture defines two random outer boundaries, and it turns out that their distribution is exactly identical. Okay, so just the fact that these two have the same, this property implies that the boundaries of these objects are the same. Okay. So this is the outer boundary. If I show you this picture, you will not be able to tell whether this was an outer boundary of a Brownian motion or an outer boundary of a percolation cluster. Okay, this is sort of some background. Now, I want to say a few words on analysis on carpets. So here is a picture of the Sierpinski carpet, which you all know. Here, the carpet is the white part, of course, and it's not the black part. And sort of the two-dimensional natural extension of the 1/3 Cantor set. And you see that this white part is connected by arcs, so you can, it's a nice set, but of Lebesgue measure 0, okay, of course. And it was, a natural question to play with, if you're coming from probability theory, to say, well, is it possible to define in this white region something that is a Brownian motion? Okay, well, is there a canonical process that would be a Brownian motion that moves around at random in this white region? Actually, the motivation to do that in initial motivation was that this Brownian motion should be, because of the scale invariance of the obstacles, should give rise to what is we like to call an anomalous diffusion, right? So that it should not have a scaling of 1/2 like a Brownian motion does, but sort of, should have a different behavior. In particular, because you have these large obstacles, you have to speed up at smaller scale in order to make it possible to go further. And so it's actually interesting because you had sort of parallel sort of descriptions. One, there were sort of very long papers of Bass and Birdsey who were just defining by bare hands, in some sense, this Brownian motion, and they were using, explicit moves like, chess moves, the moves of the how you say the horse, well, not knight, the knight. And it has sort of really explicit versions, and a bit later Kusuoka and Su, had another approach which, as often, is very powerful in order to try to define a Brownian motion just via Dirichlet forms. And basically, clearly, if you have a Brownian motion in such a domain, then you can start looking for something that plays the role of Laplacian. So here the Brownian motion, just for the record, is a Brownian motion that is basically reflected on each of these boundaries. Okay, it's not a Brownian motion that's conditioned to avoid all the holes. That would be very difficult. It's a Brownian motion that is sort of always bouncing on all these holes and using So in particular, it's easy to define it. So you see that the strategy of proof is, you first look at the Brownian motion where you, at the Brownian motion in the domain which has, you do a cutoff, you only have finitely many holes, and then you try to control what happens when the set of holes, when you add all these little holes all over the place. And you want to say that the effect of these little holes are sort of uniformly spread all over the place and will not sort of really affect, besides some sort of slowdown, the evolution of the path. So intuitively, it doesn't look, terribly difficult, but in practice, when you have to try to control this, it's unpleasant. Okay. Somehow, it's interesting that besides defining this object, it has not really been used. We are usually, when you have a Brownian motion, and especially these days, you know that you can do lots of things. You can define Brownian loops, you can define Green's function, you can define Gaussian free fields in that domain, you can try to define all sorts of structures. And this has not really, to my knowledge, pushed at all, and it might be actually worthwhile to do. Of course, the notion of Green's function itself has to be delicate, and given the fact that the Brownian motion, is living on a zero measure set, you have to be understand these things with some precision. But still, I mean, the behavior of these Brownian motion, these fractals, is quite mysterious in some sense. So in particular, the pathwise behavior, or what do the boundaries of these guys look like? What is the dimension? Looks quite difficult. Now, I want to just another background information. I want to spread. So it's a bit like when you are spreading all sorts of little pieces and you try to recollect it a bit later. Maybe I just want to say some features, basic features of conformal invariance when you are doing conformal invariance in a non-simply connected domain. So you have this Kreisnormierungssatz, the theorem. I know that Jean-Michel likes German, so I chose the German state of the Köber theorem, that packs circle domain. So I take any domain. So by Riemann's mapping theorem, you know that a simply connected domain can be mapped conformally in a one-to-one map in a one-to-one way that sort of preserves angles into the disk. Now, if you put a hole here in your domain, you're looking for a conformal map that maps this open domain, so with an angle-preserving one-to-one map that is going to map this interior of this domain into the interior of, say, a circle domain, which would be a disk where you remove another disk. And, well, clearly it will be possible to change the location by this disk by some global Möbius transformation of this disk. And it's quite easy to see that elementary, you teach this in complex analysis courses like I did this semester, which is that indeed you can do that, but then the sort of ratio between these two circles is fixed. So it's the modulus of this annulus that you get. And so you can always do that. Now, if you have two or three, or say three holes, then you have the theorem by Köber that says, well, you can actually always find a conformal map that maps this non-simply connected domain with three holes into a domain which is a disk where you have removed three disks. So each of these holes correspond to one of these three disks, and you can do that. And the proof of this theorem by Köber is actually quite simple. It's not you only have to do sort of find the right. Well, okay, maybe I don't go into details here. You can try to do some inside-outside. You can view this as a fixed point of something, and it's a nice result. And by the way, the extension of this result, so to the case where the number of holes becomes infinite, is one of Oded Schramm's initial major contributions to mathematics. And so I just want to make two comments about this theorem. The first one is that if you look at well, maybe I do another I'll do the comment here. It's not really necessary in order for this, if you look at the Koeber's proof, that this domain here is really that fat, that is really open. You know, there's this, you can wonder at what happens if these things become, you know, larger and start touching each other here, say here. Here, like this. So if you put in a little, they almost touch each other, and you put a little channel here of size epsilon between the three of them, then you can apply this Koeber's theorem, and these three disks will start, you know, touching each other, almost touching each other. If the epsilon is comparable on all three, you know, in this picture, these three disks will start touching each other, but almost touching each other, but the distance between, relative distance between them will be comparable also. And this will, you can let then epsilon go to 0. Okay? By doing this, this domain is not simply connected anymore. However, what you end up here on the other side is going to what is called a circle packing. So if you look at, you know, the circle packing theorem and its proof, I mean, there are various proofs of the circle packing theorem, but the one that sort of goes back to Koeber's ideas is basically exactly just saying, well, let's take this a picture like this, where these things come closer to each other, and this gives rise then to a circle packing on the other side. So in this idea, which also, you know, also uses ideas that Oded has played with, you don't really need to play with a, you know, connected open set already in order to have conformal invariance. You just need here some structure. So in the circle packing theorem, you're just giving a graph. So I'm not going to recall, it's just for, you give a graph, and then you have the circle packing, out comes a circle packing and something which involves conformal invariance there. So you have already here in this type of ideas that are behind the scene in Koeber's theorem that you don't really need, in order to apply ideas that are involving conformal invariance, you don't really need to play in a really open connected set. You can start looking at structures that are in some narrow part. Okay, so recently there's a long paper of Mario Bonk in Invenciones last year that shows, for instance, that if you take the Sierpinski carpet, so the white part here, and variations of this Sierpinski carpet, where I'm going to describe to you in a moment, what happens is that you can find a map of this white part into a circle domain. Of course, now you have, you know, many circles that you are going to remove because, which is, okay, you have, clearly you can't talk about conformality in this because it's not an open set anymore, this white part, but you want to say that it's extended into something quasi-conformal, and then the surprising feature, which is not so surprising if you think about that, is basically it's unique up to sort of certain trivial considerations. So it shows already that here, even though you are in this domain, which is this white domain here, which is much smaller than the complex plane, you can still, you know, do plenty of tricks involving conformal invariance. And of course, once you have a uniformization in a circle domain, you wonder whether the proof of Mario has anything to do with the construction of the Brownian motion, because constructing conformal maps has to do with constructing harmonic functions, and constructing harmonic functions has to do with Brownian motion, and so on and so on. And in particular, you see that it involves sort of a similar flavor than I mean, the proof of this type of result involves similar question than in the case of Brownian motion, because, well, you do a cutoff, you remove the small pieces, you apply Koeber's theorem, and then you wonder, you know, whether the effect of adding the smaller and smaller pieces holes is going to change the global structure or not. And you need some sort of uniform estimate that tells you that the small holes here look like the small holes there, and so that they will have locally the same perturbation effect. It's important to notice that in both these results, what you need is some very strong uniform ellipticity in some sense, which is that, you know, the relative, you know, distance of the holes with each other are sort of uniformly bounded above and below, uniformly in the domain. So it's a bit the same feature than saying that here these little channels here are of order epsilon, all the same epsilon everywhere. Everything is very natural in this setup. And, all the ideas are natural, but the techniques are quite tough. Now, if you are looking at a carpet, here, this carpet here, how do you define it? Usually you define it doing, well, you first do a discrete version, say on a graph, on a lattice, and you can look at the lattice larger and larger and view this as sort of, I mean, there are natural lattice approximations of these carpets, of course. And if there are natural lattice approximation of these carpets, you can try to look at, do other things than trying to define Brownian motion. In particular, you can define this other local random object that I showed you before, which is the percolation. And you wonder, you know, is it possible in the discrete approximation of this thing, which has plenty of holes, to do, you know, to open and close edges with a certain probability p, and wonder if there's a critical p that separates the case where there are only very, very small clusters, and where there's one cluster that invades the entire carpet on large scale. And well, at first it looks impossible to try to manage to find do percolation to find a big cluster there, because the obstacles are everywhere. You only are left with a set of measure 0. But you remember that in the plane percolation case, there is exponential decay of sizes of the clusters, and therefore, if you think a little bit about it, you will realize that yes, actually, the self-similarity of this of the holes is actually exactly what you need in order to say that probably there is actually a nice phase transition in the when you try to do percolation in the discrete approximation of this carpet. And therefore, there is, exactly as in the two-dimensional usual case, something that should play the role of critical percolation. So there should be something that is a little bit playing the role of, random subsets of the wide part, right? That you can try to explore, that try to invade everything, sort of infiltrate everything in the wide part, but they will do it only reach a certain distance. So a little bit like the percolation clusters shapes that I showed you before, you would have something like percolation cluster shapes in this domain. Now, in the previous case, in the percolation case, remember we were coloring cells in white and black and looking at the boundary of the cells. So here, if you do this in the boundary of the white clusters, say, if you do this in the Sierpinski carpet, then you see that these black holes play the roles of black cells when you're looking at clusters. And therefore, if you want to apply this, going in between white and black cells, when you color everything in white and black, at random, that is within this white part here, you see that the holes then play the roles of cells themselves. And therefore, it's a natural, this sort of two-dimensional, this picture is very natural to sort of start to sometimes color some holes in black, some holes can be actually colored in white. There's no reason to try to do that. So you can, here you see that there is a critical percolation for the clusters that try to infiltrate everything in this white part, but then the other color is allowed to jump within the holes. So the black things would be trying to connect the black holes to each other in order to create long chains. But so this means that there should exist something like a local interface process that is bouncing on the boundaries in this carpet. That should be the analog of the SLE6 process, and that should be of interest. So here you see that when you bump into a hole, So here, imagine that here there's a big hole. And you are exploring here this boundary between black and white here. And you hit this hole, and this hole is black. Okay. So what the information that you get somehow is that this entire hole sort of corresponds a little bit like a jump. It's as if you go, could go around it, and now you're here, and you have completely black stuff on your left side. So in some sense, when you bump into a hole, you have two ways to look at it. Either you say, well, I don't know yet, it's a hole, so I just view this as locally being just a small black thing. Or you can say, well, then I discover the entire hole at once. And if I discover the entire hole at once, I now have sort of my growing curve now has added a big chunk, has added a loop. Okay, so, but of course here there's a problem, which is that all the techniques that we have at the disposal in the SLE6 case, all these conformal invariance stories do break completely down, because the conformal, if I have a domain with 3 holes, it's parameterized, all domains with 3 holes are not the same. And you can't always say that I start discovering, the interface here, I'm back, and I'm still discovering the same domain. When you, which is in that case not the same, because the structure of the remaining to be discovered domain, the moduli will change continuously, and so there's no way to try to explore this. However, you still have locality, so you feel that maybe there's something might be doable, but it's still problematic. In particular here, the shape of the future jumps. So here, when you start with, these jumps will be Euclidean squares to start with, but when you start trying to apply conformal maps, they're not squares anymore, and so it's a problem. So what can you try to do? So I'm just going to very briefly say that the first attempt to try to define random fractals, so when the holes that you discover are themselves random in some sense, are random Cantor sets, and this is just meant as a very brief warm-up to some of the much nicer and deeper pictures that you'll see in Scott's talk. Okay, you have a square, you divide in 4, you toss a coin with probability P, you throw out each of the smaller squares. This one is out. Then you continue, okay, at random. And what happens is, of course, you have phase transitions, various phase transitions that occur depending on the probability to remove each square at each step. In the limit, you have a random compact set, the white thing. It's a random fractal. And the interesting, of course, if P is too large, you remove everything eventually. So this is not very, very interesting. But if P is small, what happens is that in the remaining domain here, you still have connected components, white connected components that can view it as random carpets. So in particular, when you fill in the holes, so like this, like from here you fill in all these inside holes, you define a random carpet, and you can try to wonder, what you can do in there. But here again, there are numerous problems that you hit. Is that this random fractal that you get here in the end, when you try to understand, say, only its dimension, the dimension of the connected component that is left when you remove this dyadic picture at each with probability P at each step, the dimensions of the remaining carpet, the fractal dimension is not computable. It seems the picture is very rigid. You don't have isotropy. You remove squares, so you have prefixed shapes. And as before, the conformal invariance techniques would not work in order to try to say anything about these models. So one is a bit stuck. However, it would be of interest to try to, for this type of object, to try to see already whether the techniques about constructing Brownian motion or uniformization would actually lead somewhere. Okay, so now I want to describe very briefly these conformal invariant Markov carpets that we defined with Scott. That is called, that Scott defined and that we worked on and characterized and so on. So the idea is to say that if you try to define a carpet that has a nice property had a nice property I'm going to describe to you in a moment, then you only have a one parameter family of such random carpets. And so what you want is to define a random fractal carpet, so connected subset of the unit disk, say, and you want to define such a way that the law of the picture you see is conformal invariant. So if you apply Möbius transformation to your picture, you still have the same picture in distribution. And therefore, you can define it in any simply connected domain. Okay, these are things that I give you the boundary of the domain, and then you put in some holes. And they satisfy some sort of spatial Markov property, and the spatial Markov property can be viewed like this. You have your domain, you cut out part of the domain, and then you remove all the loops that intersect what you've removed here. And what you know is that the law of what remains to be discovered is still the same fractal, random fractal modulo conformal invariance. So what this tells you is basically the following. And this is, of course, it's a very simple idea, and then the proof is sort of elaboration on this simple idea. After all, even though the technique can be sort of a bit unpleasant, is basically saying that if I have a fractal like this, I have my domain, you can start exploring it, right? And the way you explore it is you are on the boundary and you start walking inside. You can choose whatever strategy you want, whatever algorithm you want. But you walked into the inside, and each time I meet a loop, you just remove the entire loop. So one natural way would be, I start from here and I go straight, and I, remove all the loops I encounter. And what remains to be discovered, because of the previous idea, is still, well, the same fractal in distribution modulo conformal invariance. So in some sense, what you end up here is that you have a natural definition of an excursion measure on loops, which sort of corresponds to the loops that you discover when you move from here to there. So these are going to be bubbles that plays the role of two-dimensional excursion, if you want. And the question is whether there is a way to find shapes, random shapes somehow, that would have exactly the same shape in distribution, whether you discover them from here, from there, or from there, using this algorithm. And it turns out that there is just one parameter family of such objects. And so the idea is that for any dimension between these two values, so larger than 15/8, you have a unique way to define a random carpet, right, that has dimension d always, and that has this property here. So you have some sort of universal, this is probably one of the simplest way to introduce stochastic Löwen evolution and to explain why it is comes up very naturally. And what you know is that in that case, you know the dimension of the holes also, that is going to vary between 3/2 and 4/3, depending on the value of d you take there. And they are one of these Schramm-Löwen evolution type loops. So basically the theorem would be like something. There exists a unique infinite measure on shapes here that's sort of attached to a point on the boundary that have the property that if you put these shapes conformally on top of each other when you discover them like this, or whether you discover them like this or like that, or some any other way, would give rise to the same fractal in distribution. So really, this plays a little bit the same role as the decomposition of reflected Brownian motion into excursion, say in one dimension, would be playing here a little bit the same role, and we'll come back to that a little bit later, and of course in Scott's talk of excursion theory of the two-dimensional Gaussian free field into loops, level lines. Okay, so just to illustrate this, I want to emphasize that, of course, if you believe that the two-dimensional models from statistical physics have a conformal invariant scaling limit, you would expect that they give rise to these random carpets. The idea is, I told you there was this parameter, which we call the dimension there, physicists or people in Lie algebra would call it the central charge, or if you're in statistical physics, or you have always usually a parameter that you can play with, which is the Q of the Potts model or something like that, which is always the same parameter. And for some of them, and of course Stas is our main contributor, it has been proved, even though the actual theorem that states that if you take the scaling limit of the Ising model with plus boundary condition, and you look at the picture that you see, critical Ising model with plus boundary condition in a domain, that if you take the shape of the largest holes of the other color, right? So basically you're defining your carpet would be basically the cluster composed of cells which have the same spin as the boundary and that are connected to the boundary. Then when the mesh of the lattice goes to 0, this gives rise to a random picture that should converge in the scaling limit to one of these random fractals that I described to you before. So that's one example of where these things should show up. The paper is in the pipeline, I think, but maybe not quite out yet. I mean, there are a number of results that go in that direction that tells it that this will be proved soon. So these carpets are limits of some of these models here. And there's another construction that is very useful, and of course here you don't really see anything, which involves Brownian loop soups. So basically the idea is to say that you throw in plenty of Brownian motions in a self-similar fractal way, a little bit like in the Mandelbrot percolation before. You punch holes, except that the holes will have the shapes of these Brownian loops that I shown you before, and these loops are able to overlap, and you do it in a scale invariant way. This is the type of thing you get when you punch out everything. And now you look at the connected component of that remains of the white part. So you take a connecting component of the white part, and this is also one of these fractals. And of course, there's a very deep and extremely useful connection, and this is going to be the topic of the next talk, with the Gaussian free field. And I just want to mention very, briefly, and this will be, of course, you will see variations, amazing variations of that in Scott's lecture. But that if you take one of these ways to punch out, so one of these fractal carpets, like this. So we remove these holes. For each of these holes, you punch out, you toss a coin to decide if the loop here is oriented to orient this loop independently from each other. Okay. So each point here inside has an index, if you want, tells you whether the loop that surrounds them is +1 or -1. And now you repeat the procedure inside each of these loops. So you have a second layer. Okay. You can do that by conformal invariance independently in each of these loops. So now each point in the inside will have an index around it between -2 and 2. And you repeat this procedure. So in this way, you have a random function hn. After n steps, you have a random function where each point takes the value between -n and n. And the feature is that when n tends to infinity, this random function here converges to the Gaussian free field. So that this description is something that is sitting actually in the Gaussian free field very naturally. You can view these CLE4 as some sort of level lines in the Gaussian free field. But of course, I don't want to spend too much time describing what the Gaussian free field is. And actually, maybe there's a nice description that I want to mention, because I don't think that Scott is going to mention it, which is, I suppose Jean-Michel will like, because it's sort of a reminiscence of some of these old things of excursions of Brownian motion above minimum or something like that. There's another way to do it, to couple CLE4 with a Gaussian free field, which goes as following. You take this domain here, and you keep in mind that I've told you that that these fractal carpets can be explored from the boundary. So with Hao, who's sitting there, we have been showing that there was in this CLE4 case, or the carpet associated to the Gaussian free field, there is a natural way to explore the loops, which is conform invariant, and is the following strategy that you explore from everywhere simultaneously at the same speed, roughly speaking. So you try to, you try to move from everywhere. You have sort of constant pressure, if you want, of exploration from all sides. So from time to time, you'll see a loop, happening here, then this one will come here, then, it's growing everywhere simultaneously. And the striking feature is that this movie that you get by exploring these holes one after the other is conform invariant with no time change. So that in this definition, this loop here will be discovered at a certain time. So this loop here will be discovered at a certain time t of gamma. And that time t of gamma gives you some indication of some way of measuring, in some sense, a distance between this loop and the boundary in a conform invariant way. And this would be some, yeah. And now what you can do is this is what Scott and Howe and Sam Watson did. You just do this exploration here, and instead of defining the height here, I mean, to decide that the function h1 here is just +1 or -1 where you toss a coin, the function here will just be 1 minus the time you get there. So in other words, what you have is while you explore the loops, you glide down, and then when you hit the loop, you make a jump up. So there's no coin tossing here in this description. This is exactly the same description of, if I take a Brownian excursion here, one-dimensional one, and you go down like this. You glide down, and here, oh no, this is a bad picture. I take the first time you reach level minus epsilon, and the last one here, and the law what remains to be discovered here is still a Brownian bridge. So I have a Brownian bridge, you glide down, you still have a Brownian bridge. And this is exactly this type of feature of, the relation between Brownian motion excursions. You can define either toss a coin, if you want to reconstruct a Brownian motion of a one-dimensional Brownian excursions, either you toss a coin to decide the sign, or you just take the excursion above the minimum of Brownian motion, which one of the. So it has a two-dimensional incarnation here. Now I just want to make a few comments. The first comment is that both in the Gaussian free field, and particularly Gaussian free field and Ising, these CLE, these random fractals, are naturally embedded in a wider structure. Right? They are naturally embedded. There is something in the holes. You haven't seen it yet, but there is something there. However, in this description, and what makes everything work in this description, is that there is a way to explore it from the outside without knowing that what is inside. Okay, so that the carpet is actually existing on its own. Right? You don't need to know the information about what is inside in order to define it. However, and particularly in the Gaussian free field, there are plenty of other tools in the Gaussian free field bag that make it, to be very powerful, and so it's very useful and natural to add this additional structure in there. Now, I have to speed up now. So I want to say a few words and on what is now going on when you try to you take one of these random fractals, and you want to say, what can we do in there? So the first natural question, of course, is you have all these holes. So I should take another color. Don't see anything. So you have this random fractal. Is there a natural uniformization theorem in the spirit of Mario Bonk's uniformization of Sierpinski carpets that tells you that this object, this carpet, can be uniformized in a unique way into a circle domain, so a disk where you have removed countably many disks? And the answer is actually, well, the proof doesn't, you can't just say it's the same proof, because clearly you always have this problem that because you are playing with random objects, the relative distance between the holes are random, so there's no absolute uniform, way to say this hole, two neighboring holes are actually at relative distance larger than some fixed epsilon, so you don't have anything uniform. However, things are, in some sense you can, say you have exponential decay that is allowing you to say yes, in some sense, the relative sort of distance between this, the effect of adding the smaller and smaller ones that are sort of spread all over the place is not going to, make big changes in the global structure of the Koebe uniformization map. And therefore, yes, basically these fractals have a canonical version as a circle domain. That's a work in progress of Stefan with Rode with Brent Werner. So, of course, I mean, if you have my background, you say, well, you want to define the Brownian motion on there. And I would have hoped to be able to say that I've done that, but packing business sidelined me. But yeah, so that's a natural ongoing project, which is to define the Brownian motion on there, given the fact that once you have a Brownian motion, then you can start trying to play the same game one played in the domain itself again, and also try to wonder, whether this Brownian motion, this Laplacian that you would define there, has any type of, intrinsic local properties, and you can try also try to do all sorts of things. So try to define the structure sitting on this object. Now, another question is have to do with, now you have the carpet. I mentioned here this random carpet, and you want to understand what critical percolation would look like in this domain. And here, what happens is that the situation is much better than in the deterministic fractals, because precisely because of the fact that the shapes that you start imagine you try to explore do critical percolation exploration inside the carpet, and each time you hit a loop, you bump into a loop, you actually discover it, and you have this jump. However, as long as you haven't hit it, you don't know it's there, and you can still mean out over all possible shapes that remain to be discovered. And therefore, you can try to, it's a natural thing to imagine that if you put together the discovery of the percolation picture and in the carpet and the carpet itself as a process, should be a very natural process where you have some sort of backbone thing here, and then you have these loops on top of it. As it turns out, what happens is that this process where you sort of exploring inside the carpet and adding a loop each time you put on a loop have been, such processes are around already. They are actually exactly the description of construction of these carpets, these various canonical description of these carpets. And so if you play a little bit around with sort of careful stochastic analysis, what you find out is that these the natural candidates, and that turn out to be the actual true only processes that are evolving locally within the carpets, are actually the sort of natural backbones of the construction of the carpets themselves that you are using. So what turns out is that the sort of critical percolation somehow inside, so this is very vague, it is sort of a abuse of terminology, because I'm not proving that we're not proving anything like a discrete percolation picture on the carpet converges to something. What we're proving is something that there exists a unique analog, what we will be proving, put it this way, discrete analog of SLE6, which is a randomly growing process in the carpet that has locality embedded in it and conform invariance in some sense, is actually unique, and we can describe it. So it's a little bit like saying, by brute force, you declare that SLE6 is continuous percolation boundaries. And here you would be able to describe these random curves that sort of explore this thing inside here in this domain. Turns out there are also SLE curves but these other which are bouncing on each other, and this is one case of the duality that Bertrand knows well, and that Scott is going to remind you in the context of the Gaussian field a bit later. So this is one direction. Another direction that is a very natural question to go. And of course, once you have this, you can start playing the same games while wondering whether, understanding one tells you something about the other. So probably you will get some information about actually the Brownian motion itself by exactly in the same as in the whole plane. So just to conclude, I just need we started on time, so I need to finish on time. So there are a number of very natural, generalization that you want to play with. The first one is to say, well, conformal field theory plays naturally, and as we all know, conformal field theory plays very natural on Riemann surfaces. Particularly, you want to do it on compact Riemann surfaces and try to understand these things. And I guess Julien is going to play with conformal structures also. So, so far, one can define what would be these natural fractals on the Riemann sphere with sort of inside-outside type symmetry, except that you need to, add the nesting feature in order to make sense of what you're getting. But it's a bit tricky to generalize it immediately to, other compact surfaces. And in the CLE4 case, or in the Ising model case, you have a roadmap. The roadmap would be to say, I take a Gaussian free field, say on a compact Riemann surface, I define in a proper way, and I take its level lines, and this gives rise to these fractals. And you start seeing that there's something arbitrary in deciding where you put the height of the level line, and therefore there's something slightly arbitrary in the definition of your fractals, but it gives you a roadmap how to proceed. In the case of the Ising model, you could just put the Ising model on the surface and look at the boundaries of clusters, and that would also give you a roadmap. For the other fractals, it's not entirely obvious how to proceed, in particular because if you try to embed them, for instance, in the Gaussian free field, to know what is a deterministic function of what is a bit critical. Okay, so the take-home message, basically, that I wanted to convey is the following: that typically, when you are working try to work in a deterministic fractal or in a not very well-chosen fractal, then all the techniques that come out of conformal invariance are not very useful because of the fact that the fractal has is parameterized by infinitely many parameters that describe, the relative positions of the holes, and you have too many things to control. However, you have these very special carpets, random carpets, that have this sort of sponge type, that react well to conformal invariance, if you want, and for which that are good sort of examples and good, ways to start playing this idea, or trying to play in what happens when you are looking at trying to define a random structure that lives itself, okay, in a two-dimensional carpet, and trying to do analysis in there. And of course, what I haven't, hinted at, because so far the sort of information we have is not very is weak, but you will want, once you have Brownian motion and so on, there are other things you want to try to do, like, defining distances within the carpet, intrinsic distances, which in a way is sort of, in the uniformization theorem is not so far, because you have sort of the global position, relative position of the point in the uniformization picture is sort of given. So you can, well, there are a number of things you want to try to do, and that are seemingly connected with a number of other open questions around, in particular, planar maps, and which also have this question of natural canonical uniformization via circle packings, which is one of the big open problems to understand the Brownian map defined by, with a nice theorem by Le Gall and Mirmont about that show up as scaling limit of discrete randomly chosen planar graphs that should give rise to a random two-dimensional metric, and whether what is the relation with all these circle packing and so on. So this was a bit went maybe in various directions. I didn't want to focus on one specific result, rather sort of giving you the global picture, hoping that also it may help you sort of in the oncoming probabilistic talks. And again, I want to conclude that sort of my final act as an Orsay mathematician. I'm extremely proud to have been and part of this wonderful lab, and that Jean-Michel is sort of one of our symbol of. Thank you.